Hello everyone, welcome to another tutorial on Geeks for Geeks. In this video, we are going to understand the program which adds all greater values to every node in a given binary search tree. First, let us take an example. A simple method for solving this is to find sum of all greater values for every node. This method would take big O of n squared time. We can do it using a single traversal. The idea is to use following BST property. If we do reverse in order traversal of BST, we get all nodes in decreasing order. So we do reverse in order traversal and keep track of the sum of all nodes visited so far. Then we add this sum to every node. Now let us see the algorithm. Let us also have a sample tree to test our algorithm. We pass the root node, which is 11, and 0 to sum to modify BST util function. As root is not null, we recur for the right subtree. So we pass the right child of 11, which is 29. Again, as root is not null, we further pass the right child of 29, which is 40. Again, as root is not null, we pass the right child of 40, which is null. So root will now point to null. As root is pointing to null, we return to the previous call. Next, we update sum to sum plus roots data and roots data to sum. So sum will be equal to 40 and root will also be 40. Then we pass the left child of 40, which is null. So root will point to null. As root is pointing to null, we return to the previous call. Execution for node 40 is over. Execution for root equal to 29 is resumed, and now we update sum to sum plus 29. So sum will be equal to 69. We update roots data with sum. So 29 will be replaced by 69. Next, we pass the left child of 69, which is null. So root will point to null. As root is pointing to null, we return to the previous call and finish execution for node 69. Execution for root equal to 11 is resumed, and now we update sum to sum plus 11. So sum will be equal to 80. Also, we replace 11 by 80. Next, we recur for the left subtree. So we pass the left child of 80, which is 2. As root is not null, we pass the right child of 2, which is 7. Again, as root is not null, we further pass the right child of 7, which is null. Now, as root is pointing to null, we return to the previous call. We update sum to sum plus 7 and roots data to sum. So sum will be equal to 87 and 7 will be replaced by 87. Next, we pass the left child of 87, which is null. So root points to null. As root is pointing to null, we return to the previous call and finish execution for node 87. Execution for node 2 is resumed, and now we update sum to sum plus 2. So sum will be 89. We update 2 to 89. Next, we pass the left child of 89, which is 1. So root points to 1. As root is not pointing to null, we pass the right child of 1, which is null. As root is null, we return to the previous call. we update sum to sum plus 1. So, sum will be 90 and 1 will be replaced by 90. Next, we pass the right child of 90, which is null. As root points to null, we return to the previous call. Execution for all the nodes is over and we have the final greater sum tree. Now, let us have a look at the time complexity of the program. This code will run in big O of n complexity. Here, n are the number of nodes in the binary search tree. With this, we come to an end of this tutorial. For any doubts or suggestions, please leave them in the comment section below. Thank you for watching.